Okay. So consequence. So this is the corollary. This equivalence relation can be used to partition S, the original set, S into equivalence classes. So in an example, original S is A, B, C, D. Then we find that A and B are related. And then C and D are related. So this group G defines a relationship. And then this relationship partitions the set S into two groups. Each one has two items. Is that okay? Okay, now we are ready to talk about Burnside. So what is Burnside's theorem? So then Burnside's theorem counts the number of equivalence classes in this scenario. Okay. So Burnside says, so the number of classes, number of equivalence classes is equal to 1 divided by the size of this big G times the summation of pi in this G, and notation psi of pi. Okay. Number of items are invariant. Invariant in pi. Okay, so this is a result, okay, but let's take a look. So this result has some notation that we need to describe. Okay, so Burnside says, okay, there is a formula that counts the number of classes. Okay, the formula is like this. Okay. So the formula has some parameters like 1 over the size of G. So how many permutations in the group times the summation of, for each permutation in the group, we look at a special property, a special number, which is called the psi of pi. Psi of pi counts the number of items that are invariant, that maps back to itself in the corresponding permutation. So let's do this. So let's check, okay. Let's use this example to check, okay, what happens. Okay, so this is a group, a permutation group. And then we have 4 pi. So we have pi 0, pi 1, pi 2, and then pi 3. So we have these different permutations, right? And then, okay, and then for each permutation, what do we need to do? We look at the number of invariants. Okay, so how many invariants are there? So this is A maps to A, 1, 2, 3, 4. Is that okay? There are 4 of them, so there is a 4 here. Here, A maps to B, not the same. B maps to A, not the same. But C is the same, D is the same, so we get a 2 here. Is that okay? Here, A maps to A, B maps to B, but C and D, they do not map to themselves, so we get a 2 here. Is that okay? Or in pi 3, all of them are different. So we get a 0 here. Okay? So Burnside says, let's add up all the blue numbers and then divide it by the size of G. So we add the blue numbers and then divide it by 4. So what do we get? We get 2. So there are one class here and there is a second class here. Okay? Okay. Is that okay? Now, let's skip the proof of Burnside for now. Okay. But let's see its application because it is more amazing. So let's believe in Burnside. Okay. And let's see how it can help us to solve our original problem. So for our original problem, we are going to count how many equivalence classes of the triangle colored in 2 colors, right? Okay. So let's think of it as, okay, let's think of a set S that contains all the 8 different cases that we have. Is that okay? And let's think of permutation, a group of permutations, which do the following, which describes the different operations on the items. Okay, so so we try to apply Burnside to solve our problem. So let's define a group that looks like this. So we have all these items. So the first permutation that we are going to look at is it maps back to itself. Is that okay? Now, the second permutation is like we are going to consider what happens if we rotate each one by how many? 120 degrees. Is that okay? So we are going to have something like this. So we rotate each one by 120 clockwise. So rotating this one, you get to this one. Rotating this one, you get this one. And you get this one. Is that okay? And let's consider one more permutation that rotates each one by 240. So this is the group G. Is that okay? Now, so look at this. This is a group. Okay, this is a group. This is a group. because it is associative. You apply this one to this one, you get this one. Is that okay? You apply this one to this one, you get this one. You apply this one to this one, you get this one. Is that okay? So you can check out that it is a group. Okay. And then what was our original problem? Our original problem is to find out, okay, how many classes that we have. Okay, so if a certain a certain case here, this is a certain item here, you can use rotation to get into the other item. They should be in the same. They should be considered in the same class. Is that okay? Is that okay? So, is that okay? So we mentioned that if we consider two items in S to be the same, if one can be obtained from the other by doing rotations. Is that okay? And these are the rotation operations that we are describing. Okay? So these are all the different rotations that we are describing. So if one can be obtained in the other in the rotation, then they are related. They are related. And then we are, so with this representation of S and G, what we need to do to solve the original problem is to count the number of equivalence classes defined by this group. Is that okay? Okay? So how many classes are there? How many classes are there? So we have done it, four classes. But by Burnside, how many classes are there? So if you look at it, this will be very easy. Okay. So count how many invariants are there? So there are going to be 8 here, right? There are going to be 8 here. And then how many invariants are there? How many? 2. Just all the whites and all the blacks, right? And then how many invariants here? It's also 2, right? So by Burnside, it's going to be 8 plus 2 plus 2, the sum of everything, divided by how many permutations we are talking about here? 3. So it is going to be 12 divided by 3, so it is going to be equal to 4. Is that okay? Is that okay? Now, just to make sure that we understand, we are going to change this problem a little bit. So we are going to have a new S, okay? A new S. S that contains what? All the coloring of vertices in one of the 5 colors. Okay, maybe, so we have many colors, okay. So we can have a green, so we can have a green vertex. Hey, let me see. Okay, so we can have a lot of colors. So we may have green or red or blue so let's say S contains all the different so let's consider coloring each of the vertex of a triangle with either white, black, or green, or red, or blue. Is that okay? So we now have 5 colors. Okay, we now have 5 colors. And then we consider 2 coloring to be the same if one can obtain to the other by doing rotation. Okay. Now how many distinct cases we can form? How many distinct cases we can form? So let's talk about this G of this S now. How many items are there? How many permutations should we consider? So there should be a identity, right? There should be identity, right? What else? There should be 1 for rotating 120 degrees. Is that okay? And there should be 1 that rotates 240 degrees. Is that okay? And there should be 1 that is identity. Is that okay? It's still the same as the previous problem. We just need to consider 3 permutations. 1 permutation that maps each item of S to itself. The other permutation that maps each item of S to its 120 degree clockwise result. And finally, another permutation that maps what? That maps each one to the corresponding case after rotating 240 degrees. Okay? And then now, we are asking the same question. How many different cases can we form? how many equivalence classes that we can form. Okay, so how many classes? So Burnside says, count the invariant here, count the invariant here, count the invariant here, add them up, and then divide it by 3. Okay, 3 because there are 3 permutations here. Okay? Is that okay? So how many? How many are invariant here? So how many items are there in S? So how many items are there in S? How many? 5 times 5 times 5. Is that okay? Is that okay? 5 to the power 3. Is that okay? So Burnside says, okay, here you get the number 5 to the power 3. You want to add this up. Is that okay? And this one corresponds to rotating by 120 degrees. So if something is going to be the same after it is rotated by 120 degrees, then what? Then it must be. So if something is the same as if, let's say this is A, B, C, it's the same as if it is rotated. So A becomes here, B becomes here, C becomes here, right? So this must have the same color as this one. So this has the same color as this one. They are the same, right? So this has to be the same as this one, and so on and so forth. They have to be all in the same color. Okay? So in that case, how many invariants? 5. Excellent. And how many invariants here? 5. So the number of classes by Burnside is equal to 5 to the power 3 plus 5 plus 5 divided by 3. And that's it. Okay. So it's going to be something like 45, right? Okay. Is that okay? Okay. You can have more examples. So there are a lot of examples. Let's do one more related to check our understanding. Okay. Let's do this. Okay. Okay. This time, let's consider S to be square. Okay. How many colors? Okay. Whatever you like. Let's say 6 colors. It's possible for each vertex. And again, we want to find out how many different cases that we can color the vertices such that after a rotation, after the rotation, one can become the other, they should be considered in the same group. Okay, so how many groups are there? How many classes are there? So in that case, let's apply Burnside again. But this time, what are the permutations that we need to look at? One is we do nothing, the identity permutation, right? How about the other? So we should look at rotated by 90 degrees, right? 90. Is that okay? And then we should do this. Remember, it is a group, right? So if you have rotate by 90, you can do rotate 90 and then 90 again, right? So you should still have something like rotated by 180. Is that okay? And then you should still have one more, rotated by 270. And then you find out that these are all the cases. These are all the cases that we have. Okay? And then what? And then, okay, we want to count the number of equivalence classes. Okay, we want to count the number of equivalence classes. So how many are there? So we count the number of invariants here. So 6 colors for each vertex. So the size of S is going to be 6 to the power 4, right? Okay, 6 to the power 4. So this is identity. So there are 6 to the power 4 here. Next is something. I have a coloring of the vertex but it is the same if I rotate it by 90 degrees, what will happen? Then all the four corners has to be the same, right? All the four corners has to be the same. Is that okay? So there are how many of them? So there are going to be 6 of them. Is that okay? You rotate. And then here, 270, it is also 6. But how about this one? If something, you rotate it by 180 and it is the same, what does that mean? It means that the opposite corners are in the same color, right? How many cases that we can have with the opposite corners have the same color? How many? How many? 6 square, yes, 6 times 6. So the number of equivalence classes is the number of classes is equal to, you add them all up, 6 to the power 4 plus 6 square plus 6, you divide it by 4. Okay, is that okay? So I don't know what it is, okay. So some number, okay. Maybe this is like 1, 2, 9, 6, and then 12, 48, something like 1, 3, 6, 7, 4, something like this. Okay, and then you divide it by 4. Eh? It's impossible. 7? No, this is going to be 4. Eh? Whatever. Okay, so I'm making mistakes. Okay. So this is how it is done. Okay, I will describe more examples next time because we have not got the proof for this Burnside yet. But before we conclude the class, let's do one final example. Okay. Let's make things more complicated. Let's do this. Let's do this time S. Okay. And then triangle now again. Okay. So we can have 5 colors for each vertex, the same as before. And then the operations are rotation and then flipping. We can do flipping. Is that okay? Okay. So here, how many permutations should we now consider? So we should have one that is the identity, right? One that is rotated by 120. One is rotated by 240, right? Is that okay? And there should be one that is flipped. Flipping. So I flip this. And what else? What else? I should have a flip and then rotate by 120. Is that okay? So it's not there. You remember, we want to have a group. Okay, it needs to be closed. Okay, so for any pair of operations, we need the thing to be defined. So I need to have something like I do a flipping first, and then rotate 120. Is that okay? So I need to have something like I flipped and then rotate 120. Okay, so this is the order. And similarly, I should have a flipped and then rotate by 240. Is that enough? We can, how about rotate 120 and then flip? Is it there? Okay. So A, B, C. Is that okay? So you rotate 120, you get A, B, C. Is that okay? A, B, C. And then you do flipping. Flipping. You do what? You do A here, B here, C here. Is that okay? Okay. But this is going to be the same as you are going to do flipping first and then rotate 240, I guess. Is that okay? Is that okay? So it is like flipping and then you do 240. Okay, good. It's there. Okay. And then by careful checking every pair of them, you get an operation, right? And then it is closed. It's still there. So it is a group. And this is what we need to consider. Okay, then how many groups are there? How many classes are there? So originally we don't have flipping, right? But now we have flipping. So in that case, the classes should decrease because more things will not become the same. Because we still consider flipping to be the same, right? Let's check. Okay, so here, how many of them? So there are going to be 5 to the power 3. Is that okay? So this is the same as 5 here, the same as 5 here. How many cases are there such that you do the flipping and then it remains the same? You do the flipping and it remains the same. So how many cases are there? How many? The top vertex, you can choose it freely. The bottom 2 vertex, it has to be the same color. Is that okay? Is that okay? So there's going to be 5 square. Is that okay? 5 square. How about this one? You flip and then you rotate, it needs to be the same. Well, because after rotation it is the same, the 3 vertex has to be of the same color. So there are just 5 here and there are just 5 here. Is that okay? So by Burnside, we should add them all up and then divide it by 6 this time. Okay, so let's count. Okay, so this is 125, 135, 160, 170. Is that okay? So there are 170 of them. Yeah. Something wrong. 170 cannot be divided by 6. 175? Again. Let's again. Okay. 125. You add these two. 135. 170. It doesn't make sense. Okay, let me see. Something wrong. Okay. Which part is it wrong? 哪一个？对不起，他们这两个是。你说这两个是一样的吗？还是不？这个也是5平方吗？为什么？Let me see. Oh, thanks. Got it. Thanks. Excellent. Okay. So okay. Thanks. So we get a miscalculation here. So this operation is like ABC, and then you get into this one. Is that okay? So the B does not change, and then we are just flipping A and C. Thanks. That's excellent. Okay. So what does that mean? So if I want this one to be the same as this one, invariant, then in that case, this one you can color it in any color, but A and C, you should color it in the same color. So there are 5 square of them. Thank you very much. Yeah, and then this one is also 5 square. Okay, let's do it again. Okay, 125, 135, and then it's 75, 210. So it is 210. Okay, so you divide it by 6. So 210 divided by 6 is like 35. Is it? It's like 35. So the answer, the number of classes, is equal to 35. So it drops a little bit. It drops a little bit from 45 to 35. Okay, by doing the flipping as well. Okay, thanks all. So I hope you like it. So Burnside is very powerful. Okay, you don't need to. So if things are regular, you can count it systematically by doing in another way of counting. So we are counting invariant rather than counting, looking at the cases where they are the same. Okay. Okay. Thanks a lot. Okay. So let's meet again on Tuesday. Okay.